Today we're going to look at series in sigma notation. A series is the sum of all terms of a sequence. So you're basically going to find all these terms and just add them up. The nth partial sum is the sum of the first n terms and is written as S sub n. A series can be infinite or finite. Final. That doesn't say finite. Let's try again. Finite. A series can be written in sigma notation denoted by, now remember sigma, we've talked about sigma before, and if you recall we've used this for lowercase sigma, but uppercase sigma looks like an E. You'll see this is kind of how the computer will show it. So what you're going to do is do your best to do, oopsies, I'm going to do that. I meant to kind of just draw another line coming up. This capital letter E. Now, if you could just pause the video and read over these bullet points, but I will discuss them as we do problems with sigma notation. All right, so let's talk about finding partial sums. This actually is very easy to do by hand. If I say find the fifth partial sum, what you're going to do is sub in 1, 2, 3, 4, 5, and then add up all of those different terms that you get. So a sub 1 is equal to 1 squared minus 3. So 1 minus 3, we get negative 2. A sub 2 is equal to 2 squared minus 3. Or 4 minus 3, we get 1. The nice thing is that this is explicit, so I can just keep subbing in different n values. And then I can just add them up at the end. Now, once you are finished, you take all 5 of those terms, and to find the sum of them, we just add them up. I'm going to use my calculator just to be safe. It's pretty early right now, so I just want to make sure I don't make a mistake. Negative 2 plus 1 plus 6 plus 13 plus 22 equals 40. And that would be the final answer. Let's look at the next page. Now, on the next page, you're going to see this sigma notation. When it says to evaluate and you see this sigma sign right here, actually, let me use green. When you see this right here, it will not say in the directions, find the sum. But if you see this sigma, that means sum. You have to know that. Now, how are we going to do this? You're going to use what I like to call the counter. The bottom number is the first number you sub in. The top number is the last number you sub in. But I call it a counter because you have to get every single number in between. So basically with this, I need to sub in 1, 2, 3, and 4 in order to find this sum that I'm asked to find. So you're going to start by subbing in a 1, and you're going to get 1 minus 1, or 0 for that first term. Then you're going to sub in a 2. Then you're going to sub in a 3. Oops, all of a sudden I got cubed. And be careful too, because this does happen a lot where people know what to do, but they'll accidentally write the number wrong. And I just showed you a great example of that happening. And then keep going till you get to that top number, 4 squared minus the 4. So 16 minus 4, we get 12. Now, don't forget, we have to find the sum of each of those. So then, or the sum of all four of those. So what we can do is then add these all up. That would give me what, 18, 20? I think 20. Yep, we're good. And that's how you would evaluate when there is a sigma in the problem. Now, the final part of this is writing a series in sigma notation. What is the difference between a series and a sequence? A series is when you have a list of terms, but there are pluses or minuses in between the terms instead of commas. A series is what you create when you're actually adding the terms together. So with that being said, if I wanted you guys to write each of these in sigma notation, first thing you want to do is start out with your sigma. Now, the next thing we want to do is think about how we can connect each of these to the n value. And then we don't know what this last one is. That's what we'll have to figure out. That will become important. Whenever you're using sigma notation, you are always using explicit rules. No recursive. So in other words, you have to connect the n value on each term to what we're seeing for each term. I should be able to sub in n equals 3 and get this term directly. You have to be careful that you're not thinking about what happened the previous term. You're just focused on each term individually. Well, with that being said, look at my numerators. All of the numerators are not dependent on n. Every single numerator is equal to 5. In the denominator, though, I hope you're seeing that one of those numbers is your n value, which means that the denominator of this would be 1 plus n. Now, when we do our counter, the bottom number, you always want to do n equal to 1 at the bottom if possible. Sometimes you'll see this counter starts at 0, but we really try to keep it equal to 1. And then think about what would be the last number we would sub in. Well, the last term of this is 15, and that would give us our last term. Now, they don't actually want you to find the sum of this. They just want you to write it in sigma notation. So this would be our final answer on this problem right here. The next problem, let's do the same thing. You're going to start with a sigma, and then underneath each term, think n equal 1, n equal 2, n equal 3, n equal 4, and then we don't know how far this is going to go. Now, again, we want to write this rule to the right of the sigma. And again, I'm seeing that all of these numerators are staying consistent. I'm going to write that first term as 1 over 1, but I just want you to see that all of these have a numerator of 1. In the denominator, however, I'm not seeing that. I'm not seeing that it stays the same. They are changing, and I'm trying to connect it to the n value. And you can see where you're going to have to do a little thought process. What I am noticing, and again, you want to avoid thinking recursive, but I am noticing that each of the denominators is changing by a power of 2. So if I focus on just one denominator separately, so like let's just say I pretend like that's not all there, I'm noticing that this really is 2 to the 3rd power. I'm noticing that this is 2 to the 2nd power. This is 2 to the 1st power. And technically, I could write this first term as 2 to the 0 power. Now you need to connect that power to the n value. And if you notice, it's always 1 less. So what I can do is I can say that this is 2 to the n minus 1 power. Okay, if it was just 2 to the nth power, notice that that wouldn't work because that would make this term 2 to the 4th power. But we want to subtract 1 from the n value to get that power. Now, from here, we can actually start our counter with n equal to 1 and just make sure it works. If I sub in a 1 to this formula, I should get 2 to the 0 power, which is equal to 1, and I do get that first term. However, I need to do some math here. I need to think about what am I going to sub in for n to get 128, because that number has to go on the top of my sigma. So if you don't know, you can either guess and check, or to the side, think, when does 2 to the n minus 1 equal 128? And guys, you just finished the unit where you learned how to do this. You could either write this in log form or just guess and check. If I use what I learned last unit, I can rewrite this in log form, log with a base of 2. Remember, the exponent goes on the other side, and then the 128 would go here. If I solve this, and again, you can check, use the circle of life, you'll see. If I go to my math, and then I go to log base, I can type in the 2, I can type in the 128. Now I get a 7, but note that I still have n minus 1. When I add the 1, I get an 8 for n. So that means the top of this would have a value of 8. Now check to make sure that that works. If I sub in an 8, I should get this last term. So this should be n equal to 8. So let's sub in an 8. 2 raised to the 8 minus 1 power. I'm getting 128, which is exactly what I should get. All right, final problem on here, number 5. I know these are kind of weird, but with practice, they actually become very, very easy. It's just you got to practice it a few times. Final one, we're going to write in sigma notation. I'm going to write n equal 1, n equal 2, n equal 3, n equal 4. Now, right away, I see the numerator is the n value. So what I can do is the top of this, just put n. I'm noticing the denominator is always 1 more than the n value, so I can put n plus 1. Now, the first term is n equal to 1. The last term, because of the dot, 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 that means it keeps going. This is what we call an infinite series. You're going to put an infinity sign on the top.